Hello everyone, Victor is here, your organic chemistry tutor, and in this video I want to talk about acid chlorides and what a mighty magnificent functional group that is. We are going to talk about the synthesis of acid chloride and the most typical reactions of acid chloride that you are going to see in your class. So first of all, let's talk about the synthesis of acid chlorides. There are three main methods how we are going to be making these compounds, all of which are going to start from the carboxylic acid. We can react carboxylic acid with thionyl chloride, SOCl2, this reagent over here, which is going to give us SO2 and hydrochloric acid as our co-products. Or we can react carboxylic acid with PCl3, phosphorus trichloride, which is going to give us phosphorus oxychloride and hydrochloric acid as the co-products as well. And finally, we can make an acid chloride by reacting a carboxylic acid with phosphorus pentachloride, which is going to give us our acid chloride, and phosphorus oxychloride and HCl as our co-products as well. The most common way that you are going to see within the scope of your course is going to be the reaction with thionyl chloride, so that one is definitely a must-know. The other two, they're good-to-know reactions. And another thing that I want to point out about the synthesis of acid chlorides is that occasionally you're going to see the use of pyridine as our solvent. It is completely unnecessary, yet we are still going to show it from time to time because some textbooks do show this reaction in the presence of pyridine. And with all of that in mind, let's look at the mechanism of the formation of the acid chloride from the carboxylic acid using the thionyl chloride over here. As I've mentioned a moment ago, this is the most common way of making acid chloride, so this is definitely a mechanism that you want to know. Since the sulfur atom in thionyl chloride is extremely electrophilic, our reaction is going to start by the essentially an SN2 style attack, where the oxygen of the carboxylic acid attacks sulfur and we are going to lose one of our chlorines. As a result of this attack, we are going to get an intermediate with a positive charge on our oxygen, making the carboxylic acid extremely electrophilic. And since we have a freshly formed chlorine as a nucleophile floating around, this chlorine can come in and attack our newly modified carboxylic acid like so, making a new carbon-chlorine bond, giving us the following intermediate. Now, if we are not going to be using any pyridine, then we are going to show the intramolecular interaction here, where the chlorine is going to grab this proton, electrons cascade around, and in one step we are going to end up with our target product, which is going to be acid chloride, plus we are going to get SO2, which is a gas, so it's just going to fly away, and we're also going to make HCl, which if this reaction is done neat, also going to, for the most part, form as a gas and fly away as well. However, as I've mentioned, sometimes we use pyridine here as a solvent, and many textbooks do show the pyridine there as a solvent, so in the presence of the pyridine, the mechanism is going to look slightly differently. We are still going to have the same intermediate that we have just before our last step, but now we are going to show pyridine coming in and causing essentially the same type of a cascade of the electron density that we had before, giving us our product over here. We are still going to have the SO2, but instead of HCl, we are going to have a pyridinium ion, and Cl- there is just going to be our counter ion to it, so that's going to be a salt. As I've mentioned a moment ago, the use of pyridine here is completely unnecessary, it's more of the optional thing, so to speak. It is best to do this reaction neat without solvent whatsoever. However, the reaction is typically shown with pyridine in many textbooks, that's why I also show the version of this reaction with pyridine as well. However, if you were to do this reaction with pyridine, you would have to figure out how to get rid of this salt that we have over here, and that's not necessarily the easy thing to do. Now, the other two methods that I've mentioned before, the reaction with PCl3 and PCl5, they do have a somewhat similar mechanism to the reaction with the thionyl chloride, but as the reaction with SOCl2 is the most common way how we are going to be preparing our acid chlorides in class, this is definitely a mechanism that you want to know, and the ones with PCl5 or PCl3 would be good to know if your instructor introduces them in the class to begin with. Normally, we only talk about the reaction with SOCl2, although there are quite a few other methods that we can use to make our acid chlorides. So now, when we know how to make an acid chloride, let's look at some of the reactions that we are going to see for this functional group. And first of all, I want to point out that acid chlorides are among the most reactive carboxylic acid derivatives. The delta plus that we have on the carbon in the acid chloride is extremely high, so this carbon that we have over here for our acid chlorides is extremely electrophilic. And also on top of that, chlorine is a pretty decent leaving group. So essentially that means that we can react our acid chloride with various nucleophiles, essentially replacing that chlorine. So you can think about all reactions of acid chlorides as some sort of a acyl substitution reaction, where we are going to start by reacting with a nucleophile and replacing this chlorine with whatever other group we have that we want to put there instead of our chlorine. And the general mechanism for this reaction is going to be pretty much the same regardless of which nucleophile you're going to be looking at. So we can have a general mechanism for negative nucleophiles. Those are going to be nucleophiles that bear negative charge. So for something like that, we are going to start with our acid chloride and we are going to bring our nucleophile with a negative charge. The step number one in all of these reactions is going to be nucleophilic attack from our nucleophile onto a carbon, shooting electrons onto the oxygen and making the following species. This is what we're normally going to refer to as our tetrahedral intermediate. And once we have our tetrahedral intermediate, the next thing is going to be our leaving group dissociation, where the electrons from the oxygen going to go down and kick that chlorine out of our molecule, giving us our final product, plus we're going to have Cl- floating around that we no longer care about. Now, in addition to our negative nucleophiles, we can also have neutral nucleophiles, and in that case our reaction is going to follow a very similar pattern, with the only exception that we are going to have an additional proton transfer step inside of our mechanism. So like in the previous case, we are going to start with the acid chloride, but now we are going to react it with a neutral nucleophile that's going to have an extra hydrogen that we'll be able to get rid of later on. So step number one here is still going to be the same, where our nucleophile going to attack our carbonyl, giving us our tetrahedral intermediate, but now the big difference in our tetrahedral intermediate is that the part that we have added, this part with a nucleophile, is going to be positively charged, which means that we need to get rid of that proton first before we can proceed any further. So to do this deprotonation, we're going to use whatever it is we have floating in our solution. I'm just going to say that I have a solvent molecule that's going to come in and pull that proton off, giving us a tetrahedral intermediate just like the one that we had in our previous mechanism. So the only thing that is left for us here is for our leaving group to go away, and with the help from the oxygen, the electrons from the oxygen going to go down, reform the CO double bond, kick the chlorine out, giving us the final product, plus Cl- that's floating around. So as you can see, the mechanism is extremely similar. The only difference is that we are going to have an extra proton transfer to neutralize our nucleophile after it has attacked our carbonyl and became essentially positive. Now, looking at the general mechanisms is of course cool, but let's look at some more concrete examples. And as I've mentioned a moment ago, using different nucleophiles, we can convert our acid chlorides into anhydrides, esters, carboxylic acids, amides, or even alcohols or other compounds. So let's go down our reactivity line and first see how we can convert an acid chloride into an anhydride. To do that, I'm going to start with my acid chloride and I'm going to react it with another carboxylic acid. So let's say I'm going to react it with acetic acid. The shortcut here is going to be our chlorine and our hydrogen over here going to go away as the HCl, and we are going to make a new bond between our carbonyl and one of the oxygens that we have in our carboxylic acid. So my product here is going to look like this. Now, mechanistically speaking, this reaction is going to be a reaction of acid chloride with a neutral nucleophile. So I'm going to start with my acid chloride. I will draw my neutral nucleophile so it's a little bit easier to show the nucleophilic attack. And we are going to do the nucleophilic attack from our oxygen of the carbonyl onto the carbon of the carbonyl of the acid chloride. And remember how I talked in one of my previous videos on the carboxylic acids, whenever we are going to be using carboxylic acid as a nucleophile, we are always going to be using the oxygen of the carbonyl rather than the other oxygen. And the same idea is going to work for all other derivatives of carboxylic acids. If you are trying to use them as nucleophiles of any sort, whether it's going to be an acid-base reaction or it's going to be any kind of nucleophilic attack, you always have to use the oxygen of the carbonyl and not whatever else is sitting on that carbonyl. So with that in mind, the intermediate that we are going to get in this case is going to look something like that, where I've made a new carbon-oxygen bond between my what used to be a carbonyl and the oxygen of the carboxylic acid. Now that is going to be my tetrahedral intermediate. This is a protonated tetrahedral intermediate, so I would need to have my solvent come in and deprotonate that. So I'm going to say that a molecule of solvent, whatever solvent I'm using here, going to come in, pull that proton out, and as a result of this election cascade, I'm going to get the following tetrahedral intermediate, and the last step that is left here for me is to kick my chlorine out, and that will give me my final product right away. Now, instead of the neutral nucleophile that I have over here in the form of my carboxylic acid, I can always use a negatively charged nucleophile, which in this case would be a carboxylate. Now, let's imagine the situation where I'm using my acid chloride as my starting material, and I'm reacting it with sodium benzoate, which is a negatively charged carboxylate. We have a minus on the oxygen, so in this case, the reaction is going to proceed in a very similar fashion, but we're not going to have a funky looking proton transfer in the middle. So now my oxygen is going to attack the carbonyl right away, giving me a corresponding tetrahedral intermediate, from which point we are going to lose our chlorine and get the final product looking something like that. Pretty easy. Now, what if I wanted to take my acid chloride and convert it into some sort of ester? How can I do that? Well, in this case, we're going to use the same principle as before. The chlorine atom over here is going to be my leaving group, and the oxygen-containing moiety that I have over here is going to be my nucleophile, which means that I can either use an alcohol, which is going to be an example of a neutral nucleophile, or I can use the corresponding alkoxide, which is going to be an example of a negative nucleophile. Doesn't matter which I choose in this case, the product is still going to be the same. The only difference is going to be an extra step in the mechanism for the neutral nucleophile. So let's say for the sake of this example, we are going to go with the negative nucleophile, which is my alkoxide. I'm going to start with my acid chloride, and right next to it I'm going to draw my negative nucleophile, my isopropyl oxide, which will have, let's say, something like sodium as the counter ion. Now, of course, like in any case of the alkali metal, this sodium is really irrelevant to us, so it can be sodium or potassium or lithium for what I care, doesn't really matter for our purposes. The first step here is going to be the nucleophilic attack from our nucleophile onto the carbonyl, kicking the electrons from the double bond onto the oxygen like in the previous case, giving us a tetrahedral intermediate that's going to look like this, and then from here our leaving group is going to go away, making our final product. Alright, how about one more example? What am I going to do if I'm going to start with my acid chloride and I want to convert it into a corresponding amide? Well, in this case, the idea is exactly the same as in the previous case. We have our chlorine as a leaving group, and we have this nitrogen-containing guy over here as our nucleophile. And since nitrogen with the negative charge is extremely basic and reactive, it is probably a good idea to go with the neutral nucleophile in this case, which means that my nucleophile here should look like something like that. Now, mechanistically speaking, as always, we are going to start by taking our acid chloride here and reacting it with my nucleophile, this nitrogen-containing compound, right away. So we are going to have our amine coming in attacking our carbonyl, giving us our tetrahedral intermediate, and here is something very important. These reactions are always done in the presence of two equivalents of your amine, and the reason for that is that amines are fairly basic. So now it's not going to be just some random molecule that comes in and pulling my proton off, it is actually going to be the second equivalent of my amine that's going to come in and deprotonate my intermediate, giving me the following molecule and an equivalent of the protonated amine. Then from this point we are going to have our leaving group dissociation like always, giving us our final product. So if I didn't have this additional equivalent of my amine that I have here, then the HCl that's going to be the co-product in the reaction on any reaction of acid chlorides would start reacting with your initial amine, because amines, well, they are basic and HCl is an acid, and this way it's going to start eating away your starting material, which means that if you don't have 2+ equivalents of your starting amine, you are only going to be able to accomplish this reaction 50% of the way. This is a fairly common exam question, so remember that it's got to be 2 equivalents of your amine or excess of amine, which means for our purposes pretty much the same. We have more amine than we technically need, but actually we need more of it because it is going to be acting as a base in this case. So some instructors are going to say 2 equivalents, some instructors are going to have excess, but in any case you always need to have more than 1 equivalent of your amine, otherwise, as I said, your reaction is only going to proceed 50% because HCl that is formed here as a co-product is going to start eating your amine away and essentially decreasing the amount of amine that you have available in your reaction mixture. Now, another fairly important reaction of acid chlorides that you are going to see in your class is going to be the reaction with organometallic compounds. And whenever we say organometallic compounds, usually what we are going to mean by that is either organolithium compounds, so R, lithium, or the Grignard reagent, which is going to be your R magnesium halide, so R magnesium acts like R magnesium bromide or R magnesium chloride, something of that sort. So here is how this reaction going to go. We are going to start with our acid chloride, and let's say as my organometallic compound I'm going to use phenyl magnesium bromide. I could use either the Grignard reagent, which is our magnesium halides, or organolithium compounds. For our purposes they are pretty much interchangeable here. So Grignard reagent is a very powerful nucleophile, so as we would expect, it is going to react with our carbonyl, kicking electrons onto the oxygen like so, making a tetrahedral intermediate and new carbon-carbon bond over here. Now, like in any reaction that we have seen up to this point, the electrons going to go down and we are going to lose our leaving group, which is of course a chlorine atom, giving us a ketone. But here is the thing, ketones can also react with the Grignard reagent, which means that as soon as we have our ketone formed, the Grignard reagent is going to immediately react with that, doing the direct nucleophilic attack on our carbonyl, making another carbon-carbon bond, and after you are going to do your acidic workup, we are going to end up with the corresponding alcohol. It's going to be a tertiary alcohol. So remember, when it comes to organolithium compounds and Grignard reagents, they react with acid chlorides twice. Now, if we look at the kinetics of each of the nucleophilic attack, the first nuclear attack by the Grignard reagent on acid chloride is extremely fast. Not only fast, but also quite exothermic, so if you're not careful, your reaction mixture is going to end up on the ceiling of your fume hood. And since ketones are less reactive than acid chlorides towards the nucleophile, the second nucleophilic attack here is comparatively slower than the first one. So theoretically speaking, it is possible to stop at the formation of the ketone and not proceed any further. However, experimentally speaking, this is not an easy feat to accomplish, and catching that point where your reaction mixture has reached the ketone but hasn't quite started reacting further is very difficult experimentally. And while some of those reactions have been reported, and in some cases they even give decent yields like 60-70% yield, stopping a reaction only after one addition is not a reliable way of making a ketone, and because of that, most textbooks do not even mention that you could potentially stop this reaction after the formation of the ketone if you're using pure organolithium or Grignard reagent. So unless your instructor specifically talked about the possibility of stopping this reaction in the middle at the formation of the ketone, please remember that this reaction has to happen twice and the final product is going to be a tertiary alcohol and not a ketone. It is really difficult to stop at the formation of the ketone and not have reaction proceed further. However, if you do want to make sure that you are going to stop at the formation of the ketone, instead of organolithium or Grignard reagents, you want to use Gilman reagent or organocuprates. In this case, we are going to start reaction by taking our acid chloride as usual, but instead of pure organolithium compound or a Grignard reagent, I'm going to take a corresponding cuprate, diphenyl lithium cuprate in this case, which, similarly to other organometallic compounds, going to react with your carbonyl, electrons go up, gives you the corresponding tetrahedral intermediate, will lose our leaving group, making a ketone, which will not react with organocuprate, which means that you can stop at the formation of the ketone and get that product reliably. And finally, the last reaction that I want to talk about is reaction of the acid chlorides with complex hydrides. So whenever we are talking about our complex hydrides, typically we are going to be referring to two species. That is going to be lithium aluminum hydride or sodium borohydride, which for our purposes of this reaction are completely interchangeable. They're going to react with the acid chloride in exactly the same way, giving the alcohol. So if I start with my acid chloride and react that with my lithium aluminum hydride, I'm going to end up with the corresponding alkoxide, which after the acidic workup would give me the primary alcohol. Now, mechanistically speaking, we're going to start our reaction as always by taking our acid chloride and reacting it with lithium aluminum hydride. So the structure of lithium aluminum hydride is going to be the following. We have aluminum that is surrounded by 4 hydrogen atoms. We are going to have a formal negative charge on our aluminum, and we are going to have lithium as our counter ion here. You should remember this reagent from the time when you were talking about aldehydes and ketones in your course, because this is a very common reagent for the reduction of those as well. Now, as we know, lithium aluminum hydride is a source of very nucleophilic hydride ions. So we're going to say that the hydride comes in and attacks our carbonyl pretty much in a similar way how we have seen this attack happen for any other nucleophile today. This is going to give us the corresponding tetrahedral intermediate, and as soon as we form that, we are going to immediately kick the chlorine out, giving you the aldehyde. Now, as soon as we form this aldehyde, we still have lithium aluminum hydride present in our mixture, so another equivalent of lithium aluminum hydride, or whatever was left from our first equivalent, going to come in and attack again. For the simplicity's sake, I'm just showing a fresh equivalent of aluminum hydride here, so this guy is going to come in, attack our carbonyl again, giving me an alkoxide that's going to look like that. Now, at that point, we no longer have anything electrophilic in our molecule, so the only thing that is left for us is to do the acidic workup and protonate that negatively charged oxygen. So I'm going to bring my aqueous acid. That aqueous acid is going to protonate my alkoxide, giving me my alcohol. And of course, these two hydrogens that I have over here on my alcohol now can be implicit, I don't have to show them, so I can as well just show my molecule like this. So remember, whenever you are treating your acid chloride with either lithium aluminum hydride or sodium borohydride, you're always going to end up with the primary alcohol as your final product after, of course, the acidic workup. Now, is it possible in this case to stop the reaction after the formation of aldehyde and not have it being reduced all the way to the primary alcohol? Well, yes, we can do that. However, we cannot do that with either lithium aluminum hydride or sodium borohydride. We'll have to use a different reagent. In order for us to stop at the aldehyde, we would have to use bulky complex hydrides, and probably the most common one is going to be tributoxyaluminum hydride. If I take my acid chloride and treat it with my lithium aluminum tributoxyhydride, I am going to end up with the corresponding aldehyde. But the trick here is to remember that this reaction has to be done at a very low temperature. If your temperature is not sufficiently low, the reaction is just going to go as normal and you are going to end up with your alcohol. Some instructors do pay a lot of attention to the experimental conditions like temperature. Some instructors will just want you to remember the reagent. In either case, remember that this reaction got to be done at low temperature, so even if your instructor doesn't mention that specifically in your class, that is still something that we expect students to know for the purposes of the MCAT or for the purposes of the ACS exams and any other standardized exams of that sort. And there you have it. Now you know all must-know reactions of acid chlorides, so you can go and show what you know on your homework or the next exam. And as always, thank you for watching, and if you like this video and learned something new today, you can show it to me by hitting the like button, subscribing if you haven't done so, and leaving me a comment below. Check out this video next, and I will see you next time.